This is Math 145, Section 6.1 Notes. And this is a pretty neat section. What we're doing here is we're applying the ideas of mean and standard deviation and those statistical measures to the outcomes of probability experiments, like rolling two dice and seeing what the sum is, right? So we're going to talk about random variables. In fact, we're going to talk about discrete random variables. We're going to define those, of course. And then we're basically going to do problems like, what is the mean of the outcomes when you roll two dice 100 times and you want to figure out, say, their sum, okay? And this also leads us nicely into Chapter 8, which unfortunately we're not going to get to this semester, but that's a big reason why Chapter 6 is here in the book. But let's start off thinking about this thought bubble and the little introductory paragraph. So think about, what would you expect when you buy a lottery ticket, right? How about, what's the standard deviation of scores when you play a dart game with a friend, right? That's the kind of thing we're talking about. Think about rolling two six-sided dice. We have looked at the probability of getting a sum of 7 or two even numbers or whatever. What do you expect from a long string of trials? Let's say I rolled those two dice 100 or even 1,000 times. What would I expect, say, the average sum to be? That's the kind of thing we're asking ourselves. What's the standard deviation of all those trials, right? How spread out are those numbers that I would be getting out? Let's define a random variable. It's simply a numerical measure of the outcome of some probability experiment. So its value is determined by chance, right? Random variables are denoted using capital letters like X. The thought bubble has us consider, for the two dice, can you think of numerical measures you might get? Can you now think of things that numbers that you would get out of rolling two dice? What kinds of things might you investigate? Pause it here and then come back to me. I pictured adding up the two dice. That would get me a numerical measure of the outcome, wouldn't it? Or maybe, what if I subtracted the two dice, right? You'll notice Chapter 6 is about discrete random variables, so let's investigate that a little bit, just kind of review this. From way back in Chapter 1, we talked about discrete versus continuous variables. And remember, we talked about how a discrete random variable is going to have a finite or a countable number of values. The values of a discrete random variable can be plotted on a number line with space between each point. As like we're talking about, 3, 4, 5, 6, right? There's space between these two, 3 and 4. There's space between. Okay, a continuous random variable, and on the other hand, is infinitely many values. The values of a continuous random variable can be plotted on a number line in an uninterrupted fashion. So here we're talking about continuous random variable could not just take the integer values 3, 4, 5, and 6, but could take any of those values in between. So we are talking about only discrete random variables here, thinking about how the possible sums of two dice is going to be discrete, isn't it? The possible sums of two dice has to be 2, right? 3, 4, 5, all the way up to 12, but you're not going to get 10.5 for any two dice sum, right? So we're talking about discrete variable, and that's why we're talking about that example here. Why don't you do number 1? Come back to me and we'll see how we all did. These are my answers for A through D on number 1. Let's go over them really quickly. We're just asking ourselves which are discrete and which are continuous. Number A says the number of cars that travel through a Burger King drive-thru in 1 hour. I'm thinking about, what are the possible answers that I could come out right? I sit in front of a Burger King drive-thru. What are the possible answers? What are the possible numerical measures that I could end up with, right? I sit there an hour, let's say 60 cars goes by, right? Next hour, maybe 61, right? Next hour, some other integer, right? There's never 60.45 cars. Can't be. So we're talking about a discrete variable. Letter B, the speed of cars on a highway. This is going to be continuous because you could have numbers like this. A car could be going 70 miles an hour. It could be going 71 miles an hour. It could be going 70.5 miles an hour. It could be going 70.75 miles an hour, right? And so what we're seeing here is that the values could be plotted on an uninterrupted fashion, and that's continuous. Letter C, for the same reason, the weights of boxes of oranges could be 40 pounds, could be 41 pounds, could be 40.3 pounds. It's a continuous variable. And then letter D, the number of free throws made in a string of 10 attempts. Very, very common setup for this these chapters. And we're talking about a discrete. Again, think about out of 10 attempts, what are the possibilities, right? How many could I make? Well, I could make 0, I could make 1, I could make 2, I could make all the way up to 10. But there's no way I could make 6.5, right? Because of the context of the situation. Therefore, we're talking about a discrete variable. Back in an earlier chapter, we talked about probability models. Now here we're going to talk about probability distributions. It really is the same thing we talked about before, but we are going to say the probability distribution of a discrete random variable x provides the possible values of the random variable and their corresponding probabilities. You'll usually see this in table form, but you very well could see an actual equation or even a graph. But usually you'll see tables like what we have down here. And this is number 2. Now it is asking us, why are the following 2 tables not proper probability distributions? But they do take on the form of a table, as you'll see in number 3. Number 3 really is a proper probability model, or proper probability distribution, as I should call it. And it basically has each and every value that x could take on and their probabilities. Okay? And we'll talk about that obviously in number 3. In number 2, we're really just reviewing what we had done before with probability models. And what we had said before is that a probability model basically, by definition, is going to have all probabilities, be values between 0 and 1, right? And all the probabilities will add up to 1. And if those 2 things are true, then you've got a proper probability distribution. And if not, then you don't. So why don't you really look quickly at number 2, A and B, and try to figure out why they are not proper probability distributions. Okay? So what I saw here on part A was this probability. This is telling me the probability that x is 4 is negative 0.15. Well, that can't be, because probabilities can't be negative, right? So that's the problem there. And on B, I look at each one and they all are numbers between 0 and 1, those probabilities, that is. So I'm not worried about that, but I noticed that the sum is actually 0.9, isn't it? And that's not equal to 1. So what that means is either they messed up the probabilities or they left out some value of x, right? If the sum of all those probabilities is not 1, then there's something else that could happen. And it's not in the table. And so this is not a proper probability distribution. Okay? We are going to learn how to display these probability distributions, and what we're basically going to do is make essentially what looks like a bar graph, but instead of a nice fat bar, you just have vertical lines above each value to denote their discrete nature, I guess is why they do that. Okay, so on number 3, we're going to draw a graph to display the probability distribution. This is, by the way, data from Netflix. It is the number of movies streamed from Netflix in a month. And let me erase all this other junk down here that I was using earlier. Now, I want to talk about this. What does this mean? This means that of all the data, let's say the last month of customer data that Netflix had, this means that 6%, that's this 0.06 here, of the customers streamed 0 movies that month. Right? Going down the table a little bit more, let's look at the x value of 3. It's telling me 10% of the customers that month streamed 3 movies. And the question is, what does the general picture of number of movies streamed look like? And that's what our little data display will do for us. Let's draw, just like a bar graph, two axes. We're going to label the bottom one number of movies, and that's x's. And then we'll name the vertical one probability. And again, that's the p of x values, isn't it? And just to, notice how my data looks like, my p of x values go from about 0, right, to 0.58. So I'm going to maybe go from 0.2, 0.4, 0.6. Make a nice scale like that. And the number of movies, I'm going to offset the 0 like we did on bar graphs so that it doesn't get obscured in the vertical axis. Then I've got my number of movies, 0 through 5, labeled there. And simply put, I'm going to try to draw just a single vertical line above each one of these number of movies numbers to indicate the probability. So for x value of 0, p of x is 0.06, so maybe there, right? Number halfway to 0.2 would be 0.1, right? And so I'm not even going all the way up there. I just, very little tiny line there. It has to go to 0.6. All right. When x is 1, p is 0.58. That's why I got such a long one there. When x is 2, p is a little over 0.2, right, at 0.22. When x is 3, I get 0.1. Let's try to do it that. Try to make it a little bit bigger than that 0 line there. But again, it's a little hard when they're so tiny. Ooh, 4 being tiny, tiny, tiny. And then 5 is even tinier, isn't it? I like to put also a nice closed circle on the tops of each of my lines. Just makes it look a little, more finished. I don't know, but that is our data display. Perfect. We get to some pretty neat parts of the statistics going on here. I want to know, what is the average number of movies streamed, right? Wouldn't that be a good thing for Netflix to know? And maybe we could think about standard deviation, right? What does standard deviation tell us about these numbers? First, we have the definition of the mean of a discrete random variable, simply given by this formula. Mu of x, we're going to use mu for the mean, just like we had introduced in the previous chapters. And then what we're going to do is we're going to take each x value, multiply it by its probability. That's what this x times p of x means. And do you remember that sigma that says add up everything? Well, that's what we're going to do. Here, of course, it goes on to define x is the value of the random variable and p of x is the probability. And, another thing, this is also called the weighted average or the expected value of the random variable. So let's do number 4 together. Simply put, it says find the mean number of movies streamed from Netflix in this month. And just like before, I have my x and my p of x. I'm going to label it mu sub x. And just for kicks, I'm going to write down that formula. And that formula says take each x value, multiply it by its probability. So I started off by taking the x value 0, multiplying it by 0.06. And then I'm going to add to it the next x value, 1, times its probability. I'm going to add to it the next x value, 2, times its probability. I'm going to add to it the next x value times its probability, plus the next one times its probability, plus the next one times its probability. And you add up all those, and you're going to get the mean number of movies streamed that last month. Okay, go ahead and do that calculation and come back to me, and we'll see what we get. I got 1.49. Now, as far as units, this is a number of x just like these x's here, right? All we really did was we took a whole bunch of these x's and averaged them, really. So that is number of movies. So I'm going to write that the mu sub x equals 1.49 movies. Don't forget about the units. It's important. What does this tell us? Well, it basically tells us the number of streamed movies per month on average, or the mean number, right? This is a neat little worksheet, expected value of a lottery ticket. We won't be doing it, but it's a neat little guy on STL Math if you're interested. And if you do any of these worksheets and you need some talking about it, you know where to find me. Okay, next up, standard deviation. A little bit more complicated formula, but nothing we can't handle. Remember, standard deviation tells you how spread out the data is. So what we're doing is measuring how close the data is to that mean value, right? So here we've got our formula. Standard deviation of a discrete random variable is given by this formula. Again, we're using sigma for the notation. And I've got that crazy looking formula. It basically tells me square each x value, multiply it by its probability, add those up, and then subtract off the mean that you just calculated squared. Once you do that, you got the variance. If you square root it, as the formula says, you get the standard deviation. I'm going to go ahead and do number 5. It tells me that this is my Netflix data. It says complete the table to find the variance and standard deviation. So again, it's just one of these, like these, we did this before back in chapter 3 when we did standard deviation. Again, I had this big long table and we just followed it through, and here I go. All right, I've got to square my x value and multiply it by its probability. Now in this case, that's just 0 because x value is 0. And then when x is 1, I got 1 squared times 0.58, which of course is just 0.58, isn't it? Then I got 2 squared times 0.22. Well, that's 0.88. 3 squared times 0.10. That's 0.9. Make sure we don't lose a decimal. 4 squared times 0.03. What is that? 16 times 0.03? That would be 0.48, wouldn't it? And 5 squared times 0.01 is 0.25. Now, add up all those guys. I added them up and I got 3.09. Now, the variance says take that 3.09 that I had before and subtract off mu squared, right? So here, I'm going to write this up here, over here. Variance equals this 3.09 minus the mu that we had before, which I remember is 1.49 squared. And let's see what that is. Then, simply put, we're going to square root it, and we're going to end up with a standard deviation. Okay, so when I took 3.09 minus 1.49 squared, I get 0.8699. And I'm going to go ahead and just, that is the exact answer. I did not round that at all. I'm going to go ahead and write that whole answer down. Now I'm going to square root that, which for my calculator, I have that 0.8699 down, right, calculated already. And then I went second, and then the x squared key on the left-hand side, and then I did second, and then the negative sign in the number pad, whose second function is ANS, as in previous answer, and then I hit enter. And I'm going to round this one to one more decimal place than was given in the values of x. We've done this kind of thing before, haven't we? So you look at your values of x and say, these are whole numbers, so I need one more decimal place than you would have in a whole number, which would be the 10th decimal place. And so now I will tell you my actual answer, that I got in the calculator was 0.93268429881, and there'd be more to it. That's just all the calculator could give us. But I need to round it to the 10th. So I'm just going to write standard deviation is about 0.9. Excellent. We also need to talk about a little bit, what does that mean? So our standard deviation being 0.9, think about this. You've got all of these various different customers, right? And each customer streams a different number of movies each month. So on average, the customers as a group stream 1.49 movies a month. That was, again, the mu. What this 0.9 says is, again, if you think of every customer's number of streamed movies as a data value, then we're looking at comparing that data value for each customer to the mean of 1.49 movies. And what we're saying is that on average, customers are 0.9 movies away from the mean of 1.49 movies. So I do have this lovely little worksheet here. Again, if you want to work over the worksheet and then email me questions and whatnot, I am not requiring paper worksheets this semester, but it's a very interesting exploration, and it gives you some good practice for expected value and standard deviation. However, you'll get a lot of that practice in your homework as well. Now, I do not want you to do these things by hand, all right? So please do remember that. I have instructions on how to do it on the TI calculators. I have instructions on how to do that stuff on StatCrunch. Make sure you practice on the calculator or StatCrunch, whichever you prefer, but please do not think you need to do all that standard deviation stuff by hand, even if your MyStatLab homework tells you to. Number 6, just one more thing to do. Again, I've got this Netflix data that I'm using. I'm going to answer these following questions. Why don't you go ahead and look at this data and answer A, B, and C and see what makes sense to you. And then, of course, pause me down here and come back to me. All right, for number 1, it says, what's the probability that a randomly selected customer streams at least 3 movies a month? First of all, I wrote down probability of at least 3, just so I kind of get down from the question and kind of a quote of the probability event that I'm interested in. And then I start to think about, well, what does at least 3 movies means? In this context, it means 3, 4, or 5. And so I've written that is equal to the probability of 3 or 4 or 5. And you'll notice I have my ors underlined there, as I always do. And then I say to myself, well, wait a minute. If a person streams 3 movies, they cannot stream 4, right? If they stream 4, they cannot stream 5. So these, streaming 3 movies, streaming 4 movies, or streaming 5 movies, are mutually exclusive, aren't they? And so the probability that 3 or 4 or 5 happens is equal to the probability that 3 happens plus the probability that 4 happens plus the probability that 5 happens. All those probabilities are directly in the table. And so I simply take them, add them up, and I get 0.14 or 14%. You can apply this probability similar to the way they phrase the question and say to yourself, if I randomly selected a customer, then the probability that they streamed at least 3 movies last month is 14%, right? You could also just say 14% of all customers stream at least 3 movies a month. It's basically an equivalent way of saying that. Let's look at number 2 really quick, letter B really quickly. What's the probability that a randomly selected customer streams 1 or 2 movies a month? Same basic thing. The probability of 1 or 2 is exactly what the question asked me for, but I know that those 2 things are mutually exclusive, so I can add up those individual probabilities, which come from the table, and I get 80% or 0.8, right? So again, the probability that I randomly select a customer and that customer has streamed 1 or 2 movies that month is 80% or 0.80. Last one, letter C. What's the probability that a randomly selected customer streams 4 or more movies a month? Well, what does 4 or more mean? It means 4 or 5 in this context. And again, those are mutually exclusive, so I can add up those probabilities, which I get from the table, and I get the probability that a randomly selected customer streamed 4 or 5 movies, or 4 or more rather, is 4%. Perfect. All righty. And that is 6.1. We are going to use these ideas in 6.2